Hello, everybody. Harry Potter here. Okay, just kidding. It's not Harry Potter. It's actually Barry Potter here from Hogwarts, here to teach you some linear algebra. So we're continuing in our chapter 5 vector stuff. So now we're going to talk about the distance between two vectors. The distance between two vectors. So we all know from regular, I don't know, you should have done this somewhere in algebra, pre-calc, or maybe even before pre-calc. The distance between 2 points is this here is the distance formula. You've seen this a million times, which is also the distance between two vectors, because it's the distance between the tips of these two vectors. There's one vector has the tip of one vector is v1, v2. The tip of the other vector is u1, u2. And we're looking at the length of this dotted red line, and that's the distance formula: u1 minus v1 squared plus u2 minus v2 squared. And that's the magnitude of u minus v. Now we just are going to take that and expand that into n dimensions, and that's it. So it doesn't, again, don't get hung up whether it means something or doesn't mean something, or looks like if you're an R9 or something. That's not important. What's important is just the definition. And like I said, dimensions, you can just think of that as variables, different variables in whatever it is that you're working with. This is kind of interesting. There are three properties here that duv is greater than or equal to 0. And that's meaning it's never negative, because it is based on a square root. It's the square root of it's this guy right here, but with more variables in it. And it equals 0 if and only if u equals v. Right. Well, if u equals v, then u1 minus v1 is 0, u2 minus v2 is 0. They're all 0. And of course, if these guys are all 0, that means that u1 equals v1, u2 equals v2, and there's your if and only if. And finally, uv is vu. It's the same thing, because it's true. Because if I would switch this right up here to v1 minus u1, yeah, it makes it negative, but once I square it, it makes it back to positive. So it's all the same thing. So these three things come very, very straightforwardly. Let's just look at some vectors. Let's see. Let's look at R4. So we want the distance between u and v in R4. So that's the magnitude of the vector u minus v. Now that vector is 3 minus 4, comma, negative 1 minus 0, comma, 0 minus 1, comma, negative 3 minus 2 is coming from these numbers right up here, which is the square root of negative 1 squared plus negative 1 squared plus negative 1 squared plus negative 5 squared, which is 25, 26, 27, 28, which is square root of 28, which, if you simplify, that's 2 rad 7. And that is the distance between two vectors. Works out very easy peasy. Now we're going to define a new concept called the dot product. And so here we go. So let's start by looking at R2. R2 is just a regular old plane. And we have a vector u, a vector v. That vector up there is the vector v minus u. And I would say that magnitude is v minus u, and basically this forms a triangle, and we know from trigonometry that this side squared, call it c squared is equal to a squared plus b squared minus 2ab cosine c. Well, that's the angle c, and that's the side c, and that's side a, that's side b, and so forth. So this is law of cosines. You should have learned this in trig or in pre-calc or somewhere along the line. And of course, we know we could solve this to solve for we could solve for cosine theta, bring everything over the other side, and divide by these two u's guys here. When I expand this out and subtract these guys, I wind up getting u1 v1 plus u2 v2. Oh, and divide by 2. Let's not forget that part. And there we go. Now the numerator of this fraction, well, I'm trying to just the numerator u1 v1 plus u2 v2, that is what we call the dot product. We're going to define that as the dot product. And so U dot V is U1 V1 plus U2 V2. That is the definition of a dot product. And if you want to put the dot product into Rn, then we get, if U is a vector, U1, U2, dot, 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 up to UN, not the United Nations, but U sub n. And V is equal to V1, V2, dot, 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 up to Vn. And don't forget, the U1, U2, UN, these are all just scalars. These are all just real numbers. And the dot product is U1 times V1 plus U2 times V2 plus U3 times V3 plus dot, 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 all the way up to UN plus Vn, times Vn. For example, if I have a vector, if my U vector is 1, 2, 0, -3, and my V vector is 3, -2, 4, 2, then U dot V is equal to 1 times 3 plus 2 times -2, because that's the first component times the first component, plus the second component times the second component, 0, 4, because that's the third component times the third component, and -3, 2, because that's the last component times the last component. And you crunch all that out, and you add it, and you get -7. Notice that a dot product just winds up being a number, just a plain old number. In other words, when I take one vector and I dot product it with another vector, I get a number. I don't get another vector. You know what I'm saying? If you multiply two things, you usually get another of the same thing you multiplied. But here I'm multiplying two vectors. I'm saying multiplying. I'm dot producting two vectors, and the result is not not another vector, but a number. That's important to remember. We're going to learn there's another type of, I'm going to say multiplication, if you will, only because they use the word product. There's something called a cross product. When you do a cross product, that does produce another vector, but we'll deal with that when we get to it. Anyways, so here's some properties of dot products, and let's take an example. So U dot V equals V dot U. That's pretty straightforward. U dot V plus W is equal to U dot V plus U dot W. C times U dot V is equal to CU dot V, and it's also equal to U dot CV. So I can pull constants in and out. 2 is sort of a distributive property that works. What is 4? V dot V equals the magnitude of V squared, and V dot V is greater than or equal to 0. Always, it's never negative. And the only time it ever equals 0 is if V is a 0 vector. So these are properties, and we're going to prove, we're not going to prove all of them, but we'll prove this one right now. U dot V, the first one, which is very straightforward. U dot V, by definition, that's U1 V1 plus U2 V2 plus dot 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 plus UN Vn. But these are just numbers, just real numbers. And we know that with two real numbers, U1 V1 is equal to V1 U1, and U2 V2 is equal to V2 U2, plus UN Vn is, Vn UN. But this, by definition, this second line here, by definition, is the dot product V dot U. So we see it's and the rest of the properties are not that hard to prove. And now what I'd like you to do now is a little exercise. Here's a vector U that's 2, -2, and V is 5, 8, and W is -4, 3. I just want you to find these 5 guys right here. Give me U dot V, figure out U dot V, W, and C is U dot 2V, and D is magnitude of W squared, and E is U dot the vector V minus 2W. By the way, I just want to point at B. It looks like there's a dot missing over here, but there isn't, because U dot V, when you crunch that out, you're going to get a scalar. So it's just going to be a scalar times this vector W. So just be aware of that. Okay, I want you to pause the video, work out all 5 of these. I will do something productive while you're on pause. butterbeer or fire whiskey? Can't decide. Okay, that's the end of our pause. Let's go now. So u dot v is 2 times 5 plus negative 2 times 8, which is negative 6. And if that's what you got, then you did it right. And we're over here. For b, so u dot v is negative 6, which we just established on A. And we want negative 6 times the vector w, which becomes 24 comma negative 18. See how fun these are? For C, so now you could pull out, notice we did something we didn't necessarily have to do, but we did it. U times 2v is the same thing as 2 times uv, which is 2 times negative 6, which is negative 12. Now I could have just multiplied the vector v by 2 and then did a dot product. But we pulled out the 2. First of all, it shows property 3 of theorem 5.3, which we just did a few minutes ago. Further, we're using the fact that we already know what u dot v is because we used it all 50 times already. Okay, now for d, so w, the magnitude of w squared is w dot w, which is just negative 4 times negative 4 plus 3 times 3, which is 25. Which means the magnitude of w is 25. The magnitude squared is I'm sorry, the magnitude of w is 5. This magnitude squared, which is equal to the dot product of w times itself, is 25. Anyway, because now we know that 2w is equal to negative 8 comma 6. So v minus 2w is 5 minus negative 8 comma 8 minus 6, which comes out to 13 minus 2. And now we're going to take the 13 comma 2 and dot product that with u, so we get 2 times 13 plus negative 2 times 2, which is 26 minus 4, which is 22. And there we go. Let's do another example. Oh, we see it right down here. Here we go. Given 2 vectors u and v in Rn, so that u dot u equals 39, and u dot v equals negative 3, and v dot v equals 79, evaluate u plus 2v dot 3u plus v. And notice here that they never gave you, they're not telling you what the vectors are. They're just telling you a couple of products. Yet we're going to be able to solve the problem despite not knowing, not being given what the vectors are. And let's see how we do that. So using theorem 5.3, which is something we just learned a bit ago, we know that this distributive property. So u plus 2v times dot 3u plus v, well, we know we can distribute. So this becomes u times the second vector plus 2v times that second vector. Now I can distribute again. This is u times 3u plus u times plus u dot, I meant dot, plus u dot v. And this guy distributes into 2v dot 3u plus 2v dot v. And factoring out all the constants, we get 3u dot u plus u dot v plus 6v dot u, which is v dot v, but v dot u is the same thing as u dot v. So I add the 6 and the 1, it becomes 7. And now I have 3u dot u plus 7 u dot v plus 2 v dot v. And I was given that the numbers in the problem. We should show you the I should really. So we were given these numbers up on top, and that's just 3 times 39, 7 times negative 3, 2 times 79, which comes out to a grand total of 254. And now I want to, if you recall, we defined dot product, as the numerator of this fraction, and this is a fraction that we use to solve for cosine theta. So now we're going to define theta. We're going to define the angle between 2 vectors based on this dot product formula thingy thing. What do I mean by that? Because what do you mean define? That's what it is. What are we defining? What I mean is that if we go into Rn, what does it mean? Because if you're in Rn, what does it mean to have an angle between 2 vectors? It's not a physical thing. So we're going to define angle based on these dot products. So here we go. So cosine theta forevermore in Rn shall be defined as u dot v over mag u times magnitude v, and that is the story. Now, the absolute value of the right side of this formula cannot exceed 1, because cosine theta, as you know, the range of cosine theta is from -1 to +1. So this dot product can't has to stay within that range. So for this definition to be a sensible definition, we have to establish that this will always be in that range, meaning that u dot v over uv, or magnitude v, will always be in that range. That's what we're trying to say over here. So let's go and do that, because otherwise, like I say, it don't make much sense. So this brings us to the famous Cauchy-Schwarz inequality, that if u and v are vectors in Rn, then u dot v is less than or equal to the magnitude of u times the magnitude of v, and here, this means the absolute value. See, the double lines here means magnitude. The single lines means good old-fashioned magnitude, absolute value. And remember what I always say: value corrupts, absolute value corrupts absolutely. I just made that up. Anyways, what I guess what I'm really trying to say is that means that if based on this inequality tells me that the top of this fraction is going to be smaller than the bottom, which is going to make it the fraction less than 1. All right, at least the absolute value less than 1. So let's look at 3 cases here. If u equals 0, then u dot v, which is basically 0 dot v, which is 0, and magnitude v equals 0. So the theorem is definitely true when u equals 0, because 0 is less than or equal to 0. If u does not equal 0, that's case 2, then let t could be any number. And if we look at the vector tu plus v, so we know that tu plus v dot tu plus v is greater than or equal to 0, because any vector, if you dot product it by itself, you get a positive amount. So tu plus v dot tu plus v, that's going to be t squared u dot u plus 2t u dot v plus v dot v, and that's going to be greater than 0. Now, let's call u dot u, to simplify this a little bit, we're going to call u dot u, we're going to call it A. The 2u dot v, we're going to call B, and v dot v, we're going to call C. And we want to obtain a quadratic inequality, at squared plus bt plus c is greater than or equal to 0. Well, because this quadratic is never negative, it either has no real roots or a single repeated root. But by the quadratic formula, that implies that the discriminant, b squared minus 4ac, is less than or equal to 0. Just before I finish the proof, I just want to clarify this line here. Because this quadratic is never negative, has no real roots or a single repeated root. First of all, what do you mean never negative? Well, because it says over here greater than or equal to 0. Okay, that's one thing. It's greater than or equal to 0. That's number one. And when I have a quadratic which is greater than or equal to 0, let's just take a look what that looks like. Well, basically, if it's greater than 0, then the quadratic, then the graph is going to be up here, not even touch the x-axis. If it equals 0, then it's going to just hit it in one spot. It's going to hit it in just one point, as opposed to, but not 2 points like a typical quadratic might do. So that's all that meant. Let's go back to the anyway. So now we know b squared minus 4ac. B squared minus 4ac is less than or equal to 0. And that means, which means b squared is less than or equal to 4ac. what I mean less than or equal to 0, because if b squared minus 4ac was greater than 0, then I would have 2 real roots. But if it's less than 0, I have no real roots. If it equals 0, I have 1 real root. Anyway, b squared is less than or equal to 4ac, which means, but b by definition was u dot v, and a was u dot u, and c was v dot v. So if we just divide both sides by 4 now, we get u dot v squared is less than or equal to u dot u times v dot v. And if I take the square root of each side, I get, by definition, I get u dot v is less than or equal to the magnitude of u times the magnitude of v, because that's what these square roots are. So it all works out. Yay, it's fabulous. And we can finally now we can finally give a legitimate definition for the angle theta between two non-zero vectors in Rn is given by cosine theta is equal to u dot v over magnitude u times magnitude v. Theta is between 0 and pi. Has to be is going to be between is restricted between 0 and pi, and we're talking about Rn, not just R2, but we're talking about Rn. So the angle between the 0 vector and another vector is not defined. So we're only talking about non-zero vectors here. This concludes part 2 of this section, and we'll record part 3 next. So see you guys. Bye. It's been loads of fun. It's been a lot of fun. Now, oops, now I'm going to end.